Grab a handful of sand, watch the grain slip through your fingers, and try to picture every grain on every beach in every desert on Earth. That's about the biggest number most of us can hold in our heads. Hold on to it, because over the next few minutes we're going to climb from a mountain you could stand on without knowing, to a storm that eats planets, to a single object heavier than the entire galaxies, until that handful of sand looks like nothing at all. And right at the top, we'll hit a wall no telescope will ever get past. So start here on the ground with the sand, and keep asking one question: how big can it possibly get? Let's start somewhere you can actually picture a mountain. On Earth, our giant is Everest, 5.5 miles of rock, thin air, a climb that kills people who aren't ready for it. For most of human history, that was the ceiling of what a mountain could be. Now leave Earth, go to Mars. There's a volcano there called Olympus Mons, and it makes Everest look like a speed bump. It rises nearly 3 times higher, about 16 miles from base to summit. But the height isn't even the strange part. Its base is so wide it would blanket the entire state of Arizona. It's so vast, and its slope so gentle that if you stood on it, the summit would sit hidden far beyond the curve of the horizon. The ground would look flat in every direction. You could be standing on the largest volcano in the solar system and never know you were on a mountain at all, a mountain too big to notice. And yet, next to what's coming, it's practically small, because from the biggest thing on a planet, let's go to the biggest thing happening on one. On Earth, a hurricane is terrifying, and it lasts a few days before it hits land and dies. That's the rule we know. Storms burn out. Now look at Jupiter. There's a storm there called the Great Red Spot, and it has never once stopped. Not for a year, not for a lifetime. When humans first turned a telescope on it, it was already raging, and it's still going now, at least 3.5 centuries later. Winds at its edge scream past 400 miles an hour, and it is wide enough to swallow the entire Earth with room to spare. Jupiter has no land, no coastline, nothing solid for a storm to crash into and break apart. So it just keeps spinning in a single hurricane, older than every country watching it, big enough to drop our whole planet inside and barely notice. A storm that eats worlds. But a storm still needs a world to sit on. What if the object itself is the thing that's too big? Here's a number to hold on to. A passenger jet can circle the entire Earth in about 2 days. 2 days to lap our whole planet. And keep that in your head, because we're about to break it. Our own sun is already past imagining. You could pour over 1 million Earths inside it and still have room. That feels like the top end of big. It isn't. Shrink the sun down to a single pixel on your screen. On that same scale, the next star, a hypergiant called yearYT, would be roughly the size of a beach ball. To fly a jet all the way around it, the same jet that laps Earth in 2 days, would take about 950 years of nonstop flight. Think about that. You'd take off before Columbus ever set sail, fly every second of every day for centuries, and still be landing after today. One star, so vast that a human lifetime of flying couldn't circle it even once. So bigger always means more impressive, right? Not quite, because the next object flips the whole idea of big inside out. Up to now, the pattern's been simple. Each thing is physically wider than the last, so let's break the pattern on purpose. Picture an ordinary teaspoon, the kind in your kitchen drawer. Scoop up sugar, and it's a few grams. Now go find a star that has died, collapsed, and been crushed into something new, and scoop the exact same spoonful. Same spoon, same volume. What does it weigh? Not a few grams? Not a few pounds? That one teaspoon would weigh around 1 billion tons, heavier than every car, ship, and skyscraper in a major city, all balanced on a spoon. Because when the star collapsed, it packed more mass than our entire sun into a ball the size of a single city. And some of these city-sized corpses spin, whoosh, hundreds of times every second, fast enough to blur. So big was never the whole story. This thing is barely wider than a town, and it makes the hypergiant look gentle, which means the real monsters aren't just wide. They're heavy in a way nothing on Earth prepares you for. And once you're chasing mass instead of width, there's one object that leaves everything else behind. That object is a black hole, but not the kind you're picturing. Start with the one at the center of our own galaxy. It already holds about 4 million suns worth of mass, crushed into a single point that light can't escape. 4 million suns. That feels like a ceiling. It's barely the floor. Out in the distant universe sits a monster called Ton 618. It weighs somewhere around 66 billion times the mass of our sun, not 66 million, 66 billion. Its edge, the point of no return, is so enormous that light itself, the fastest thing there is, would take weeks just to cross it. Drop our whole solar system into it and it wouldn't register. A rounding error, swallowed without a ripple. This is a single object that outweighs whole galaxies of stars. Remember that handful of sand from the beginning? Every grain, every star, every mountain and storm and hypergiant we've counted, this one thing is heavier than almost all of it combined. And here's the part that should genuinely bother you. Even something that vast isn't the biggest structure out there. It's just a piece of one. Because until now, we've been pointing at single things: a mountain, a storm, a star, a black hole. Zoom out far enough, and even galaxies stop being the main character. Astronomers used to think the Milky Way sat quietly in a small local group of galaxies. That felt like the whole neighborhood. Then they stopped mapping where galaxies are and started mapping how they move. And they found something unnerving. Galaxies for hundreds of millions of light years around us aren't drifting randomly. They're flowing like rivers, all in the same direction. We live inside that flow. A supercluster called Laniakea, 500 million light years across, holding around 100,000 galaxies, every one of them sliding toward a single mysterious point we call the Great Attractor. Light itself needs 500 million years just to cross our home address. And our galaxy, with all its stars and worlds and everything you've ever known, isn't sitting still inside it. It's falling toward something we still can't clearly see, which raises the obvious question: if we can't even see what we're falling toward, how much of the universe can we actually see at all? This is where the climb finally hits a wall. Here's the strangest limit in all of science. When you look out into space, you're not just looking far away, you're looking back in time, because light takes time to reach you. The farther out you look, the further into the past you see. Point a better telescope at the sky, and you don't just see more. You see older, deeper, closer to the beginning. But there's a catch, and it's a hard one. The universe is only about 14 billion years old, so some light simply hasn't had time to reach us yet, and it never will, because space itself is stretching, carrying those distant regions away faster than their light can cross the gap. That leaves us inside a hard bubble, the observable universe. And because space expanded while the light was traveling, the edge of that bubble sits about 46 billion light years away in every direction. Whatever lies past that edge, more galaxies, more superclusters, maybe more monsters like TON 618, we can never see it, not with a bigger telescope, not with more time, not ever. The limit isn't our technology, it's the universe itself, hiding most of itself from us permanently. So we've climbed as far as it's possible to climb, from a mountain all the way to the edge of everything we're allowed to know, which brings us right back to where we started, back to that handful of sand, every grain, on every beach, in every desert on Earth. Remember, that was the biggest number you could picture? So here's the answer we saved for the end. The universe holds an estimated 10 times more stars than there are grains of sand on the entire planet. For every single grain you could ever touch, 10 suns are burning somewhere out there. And each of those suns can have its own mountains, its own storms, its own dead stars crushed into cities, all of it inside a bubble we can only see part of. So next time you're standing on a beach and you grab a handful of sand, don't look down, look up, and ask it again, how big can it possibly get?